Hello everyone. We've been through the half of these chapters, and that's a good milestone for everyone. And now we look into another important sections that is about the thermal deformations, and we're going to introduce the coefficients of thermal expansion and called the CTE. And this is a very important section and totally different from before. And in summaries, the once materials is under the temperature change, the material going to have the expansion or contractions depends on the elevated or decreased temperature change. And such deformations due to thermal expansions per se can be related by this formula. Delta T, that is the temperature change. L is the dimensions, the length of the material. Alpha is called the thermal expansion coefficients. Okay, so that is a summary of this. So let's look at the example here. Consider if we have material, and for this case, okay, if we have the ambient temperature change, delta T, then this material going to deform. For example, if delta T is positive, then they're going to elongate it. Here we're assuming there's a one-dimensional elongation, okay, for simplicity. So such elongation is called the delta T. T here subscript is just to indicate that elongation is due to thermal expansion. T for thermal. And delta T basically can be formulated by this equation, and you have to memorize this one. And alpha thermal coefficients, expansion coefficient, delta T is the temperatures, and sign convention delta T positive for elevation of the temperature, negative for reductions in the change of the temperature. L is the one-dimensional dimension. Here again we assume there's a one-dimensional expansion here, so we pick up this formula. And so under this case, this material is free to deform, there's no stress there, because free to deform, there's no such reaction. However, if we consider a different case in which we constrain on the both sides, in the same time, this material is under thermal expansion. You can see this material try to expand it. However, the two constraints preventing him from changing in the dimension from the B relative to A. So if we would take this one, so and B try to deform, however this constraint try not to prevent such a deformation, so we expect the deformation reaction exists here. So such a reaction is going to cause the thermal stress, because divide P by cross-sectional area A, P over A, that is stress, and such a P loading is caused by thermal expansion. So the P over A induced the stress, and here I would say this one is called the thermal stress. More appropriate, here I just using the subscript to indicate that is a thermally induced stress. Okay, so again, the P is we can determine the P. P is how much. The P is a way to push back the such distance to maintain the end be fixed there. Okay, and so from our template, PL over EA, and so that means P is what here we have, and LEA, and this one is the in the row to equal to push back by the same amount delta T. So what's delta T? Delta T is alpha delta T times L. So through this equation, you can find the P equal to this. Okay, P divided by A, then this is the thermal stress here. Okay, so here this is the thermal expansion. So in these sections, and there's two equations, and that will be new, and both equations involve the thermal coefficient, the CTE, the coefficient for thermal expansion. And we can take a look at the one example here. So consider this material is constrained on the both sides, and then for example here we so for this example, then this material is closely fit at the both sides, so that means when the temperature equal to 75 degrees, then they just snap in here, okay? And then we want to know when the temperature dropping to -50, so that means the delta T equal to negative 125. And we want to calculate the thermal stress, okay? So the thermal stress, the concept is again, assuming if they wouldn't have such a constraint, then due to thermal contractions, because right now the temperature reduced, so the material going to contract it. So due to contractions, then we have this material going to deform like this way. So you should be able to determine the delta T. Okay, the delta T basically is thermal expansion, and then that one basically using this formula here. Okay, the alpha is the thermal coefficient we are given here, and delta T is -125, and L. So basically the contraction here is contributed by these portions and these portions together, and the length equal to L. So that is the thermal expansion. So from here we determine this value that is here. However, right now the constraint is applied here, preventing end B from movement. So we expect the reaction here to maintain the end B at that position. So from here, the role of the reaction is to push rightwards of this virtual displacement to maintain here. So RB will be equal to the deformation of the two segments. So from here we can see this segment here is the RB. So using our template PL over EA, so RB divided by here, that is the PL over EA. In the similar way for the second segment, and that is RB here, and using PL over EA, that contributing the deformation here. So the deformation contributed by the two segments in total can be formulated by this. Again, that is the displacement and deformation, and be contributed by pushing back of the RB. So RB the function and equal to delta T, delta R equal to delta T here, okay, in magnitude. So that is minus in magnitude 119.5 times 10 to the minus 3 an inch. Okay, so using this equation we can solve for RB. Okay, so solve for RB, then the reaction here, so the thermal stress in A, and that is this one, so that is the thermal stress in material 1, and this is the thermal stress in material 2. Okay, so that is like this. So we can tell, and that means the thermal stress here is tensile, because that has been maintained to stretch. Okay, now this question is, I'm going to ask you, what is the displacement at point C? You see right now the displacement C is influenced by two portions. One is influenced by thermal contraction. Okay, C, due to free kind of thermal contraction, C going to move a little bit leftward. And the second one is count to the reaction force. The reaction force actually helping C to move a little bit upward, the rightward. So we're going to determine the two pieces, and then that will give us the net displacement at C here. Okay. So the calculations you can try is this. You can simply focusing on these portions. Okay, we see. And so we pick the free body diagram on the rod AC. So we see. So this is A, this is C. And due to the thermal contraction, the delta T, say this is fixed, so delta T thermal and C relative to A, okay, and A is fixed, so basically that is equal to C at point C, okay, here. And due to thermal expansion, that is alpha times delta T times L. What is L of this one? Is LAC, okay. And you can plug in the calculation alpha equal to this and delta T negative, so this is a certain negative number here, so let me say this is a negative, say A1, okay, whatever, and in inch. Then we look at this this portion here. For this portion, this is AC, again this is fixed, and this is a reaction force RB here. And RB, this one is due to they're going to have the the deformation like this. So this deformation is called the delta, and that caused by reaction. I use subscript R, and that is about C here. So that is equal to, again using this notation, PL over EA, and the force is RB. And L, what is L? Again, that is the LAC and 12 inches, and EA, we can pick up the EA about that one. So this one, you can see this is leftward, so let me call that the number, say whatever number A2, and sorry, rightward, so that is the positive. So in this way, the net let me go back to there. So the net displacement at C simply equal to the 2 delta T, this number, and C over A, and basically this C, okay. So delta due to thermal, and plus the delta due to reaction, so basically that is the minus A1 and plus A2, okay. So basically two numbers here. So whatever the number you calculated, if the result is negative, indicating C moved leftward. If the result is positive, indicating C moved rightwards. And so that is for this example here. One typical applications for thermal stress is, for example, here we call this the gun barrel. So gun barrel, basically inside is a material, outside is another material. We want to pre-stress the barrel here to reinforce the capacity of carrying exploded force. Okay. So the question is how the manufacturers pre-stress such a core sleeves inside another material. And you can read the detail here, and I can use the following examples to demonstrate this concept. This concept demonstrated by this. Basically, the problem statement is this. We have two steel bars and two sandwich brass bar here, steel brass, and that is on their original size. And the dashed line here indicating is the center line of the pins where the two plates want to align. So here we want to manufacturers wish to sandwich the material such that the brass is pre-compressed. So we see how this manufacturing process can be done. The way is this. Initially, the steel plate make a little bit shorter, and for this example, 0.5 millimeter shorter than brass. Okay, so that is at the room temperature. They have a 0.5 millimeter difference in length. So right now you can see even only 0.5 millimeters, and any misalignment will be very hard to place the pins in. So to get the center line of the two material aligned to the same positions to allow the pin to place in, and you can see we have to get the steel longer or get the brass shorter to align to place the pins in. In this example, the strategy is to get the steel placed longer than his original length. How to do it? We simply put the steel plate into oven. We heat it up, the steel plate in the oven, and you can see right now the steel being heated up, and they're going to be elongated. Okay, so elongated to the right length that align to the brass, and then at the elevated heated condition of the steel with the brass, which is still under room conditions, then the two center line align, then we place a pin in. And under these situations, once the pins are placed, then you can see steel is still hot and brass as well, or a little bit hot. And under this situation, we simply cool down the steel at the room temperatures. Okay. So once the steel cooling down the temperature, the steel try to going back to his original shape. However, at the same time, because the brass has been engaged through the pin to the steel, so brass will also be pushed a little bit shorter. So right now the two materials is under computations in the way to get equilibrium to the certain compromise distance. So in the compromise distance, steel is a little bit longer than his original shape. The brass is shorter than his original length. Okay, so that is the thinking process. With those things in mind, then we can begin to calculate the numbers. So the first question, we want to determine how much the temperature elevation needed for steel to have the same length as the brass. Okay, so that is the things here. We know the desired thermal deformation, the deformation is 0.5 millimeters. This is a desired delta T for steel, and we plug in our temperature, the alpha, and for steel, okay, and times delta T, that is what we can calculate. And what is the L? And L, we can roughly take the 2 meters as the length. So by this case, we can determine delta T will be equal to 21.4 degrees C here. Okay. Then the second question is we want to determine the thermal stress, because right now you can see steel is elongated a little bit. So there's a tensions in steel, and brass is compressed a little bit, so the price will be in compression. So we want to determine what is the thermal stress there. Okay. So how to determine this one? And basically it's this. You can imagine this is a pin. This is a pin. Right now, both the materials are under certain loading, so that will exert the reactions, the action reactions. So, for example, on steel, and steel is under the tension. So let me change the direction here. Okay, steel is under tension, so let me say the tensions is applied on the steel, the both together. Let me call that is the tension, and let me call the P. Give a number, P star. Okay, and that is both the forces together. That is a P star, and then through the pin. And that's the actual reaction. So on the brass, they also have the magnitude P star. And again, that is the actual reaction concept. Okay. And now from here, you can see for here, let me put into here for steel. Let me change the color here. For steel, that is the deformations, and that deformation is steel and due to loading. Okay, and that is the magnitude, and again using this template PL over EA. Okay, and P is the force in steel, and L is the length, and which is 2 meters, and E is the Young's modulus of the steel given here, and A is the cross-sectional area you can obtain from the from the geometry here. Okay, from the geometry you can determine A. So okay, so basically you can have this one done, and on the other side, this is the bar, and bar has been compressed by this distance here. This is a brush. Okay, so this is a brush, delta brush, and due to loading, and that is again a PL over EA, and L E brush, A brush. Okay, so this is the steel, this is steel. Okay, so from here you can see this amount plus this amount equal to 0.5. So that means, let me say this amount 1, this amount 2, and 1 plus 2, but look at this geometry, and equal to 0.5 millimeter. In this term, that is a function of P star. This is also a function of the P star, so you can solve for P star, and P star is equal to, can be solved, is 8.8 kilonewtons. Okay, the detailed calculations is here. Okay, so once you solve for P star, then you should be able to determine the thermal stress. You simply divide the stress by appropriate cross-sectional area in each material. Okay, again, in steel that is in tension, in brass that is in compression, and like we indicated here. Okay, then the follow-up question is this: if we want to use the material to carry certain mechanical loading, for example here we want to carry a mechanical loading 25 kilonewtons, so we want to determine the total stress in each material. The total stress is come from the thermal stress. That is the thermal stress we've been calculated in the previous example here. Okay, and also the additional is the mechanical loading stress. So mechanical, and this is the cost by due to the applied loading P. So basically, once we have the two things, we simply take the summations of the two things together. Okay, here we can calculate here. So earlier we have been calculated the stress due to thermal loading. Thermal loading in steel equal to how much? 22.03. And also we have determined the thermal stress in brass and equal to minus 14.68. Okay, so that's one here. And due to mechanical loaded, and here we have mechanical loaded P equal to 25, and that will be distributed in certain way to steel and to brass. So let me call the P steel. Okay, the two together is bridge steel, and then another one is called the P brass. Okay, so PS plus PB together is equal to 25 kilonewtons, and here we have two unknowns. So that's the first equation. We need another equation. Another equation is this. You can see the two materials right now, they are pinned, so they must under the same deformation, so their deformation must be the same. So deformation must be the same. That means PL over EA for steel must be equal to PL over EA, and for brass, and here for steel basically this is PS. Okay, and for brass this is PB, and you pick up any the relative information here. So there's the second equations. So from here, the two equations together, then we can determine PS then steel is 14 kilonewtons, and P in brass is 11 kilonewtons. So from here, you should be able to determine the stress due to mechanical loading in steel equal to PS divided by the cross-sectional area of the steel. In a similar way, the P due to the stress due to mechanical loading in brass equal to PB divided by AB. Okay. So under these situations, this one PS, this one equal to 35 MPa, and this one equal to 18.4 MPa. So the total stress in steel is this number plus this number, about 57. The total stress in brass is this number plus this number is about 3.8. Okay, so that is the solution detailed in this slide, and this is a challenging example, but this basically covers all the concepts I want to deliver in these sections.